my pleasure to, we do not officially have a glaciologist as part of Cornell, but we have several people associated either with PRI or Cornell who I think if we added them all together would be a really great glaciologist. Dr. Bloom certainly qualifies, and our speaker today, Matt Pritchard, I love saying this, so I'm going to read it. Matt is a geophysicist who measures changes in the shape of the Earth. That's just a cool statement. And tries to figure out why it's shaped like it is. Matt got his undergrad at University of Chicago and his PhD at Caltech and his postdoc at Princeton. And believe it or not, he has been here since 2005 as an associate professor and geophysicist in Earth and Atmospheric Sciences. And he is, I just want to put in a plug, he is he's the first person in 50 years to take serious interest in the gigantic lantern slide collection that was left by all of our predecessors in Earth and Atmospheric Sciences, and so it's delightful that he's actually using it for science as well as for history. Matt, thank you for being here.
Great. Thank you, Warren. Thanks all you guys for coming. All right, well, it's an honor to give this talk. This is sort of my first public talk on glaciers, so it was a chance for me to learn a bunch of stuff, and it's my first time I'm going to try to show some of these lantern slides. So Art Bloom showed me how to try to focus this thing, so if it's out of focus, you can blame Art. But a lot of my interest in glaciers, I should also mention, was spurred by Brian Isaacs, who was a faculty member who has also worked a lot on glaciers, so he'll steer me right, I hope, if I say something wrong. All right, so today I wanted to really merge these two links, sort of a Cornell past history studying glaciers in Alaska, and sort of revisiting it today with satellite data, with a new set of eyes. And so we have our group at Cornell is using a lot of satellite data to try to monitor glaciers over a large scale, but satellite observations only go back a few decades. So we really want to try to understand glacier change going back to these old photographs. This is a picture from 1906 of a Cornell faculty member, Oscar von Engeln, who was developing his slides here. And this is just an amazing picture. This is, if you go to the National Geographic websites and various old National Geographic magazines, you'll see this picture in there. It was originally published back in 1909 in National Geographic, where Oscar von, I guess what people called him, wrote an article on how to take pictures using these really old cameras that use glass plates for negatives as well as film negatives, that the cameras were capable of doing both. And you know, it's very difficult to get the focus and especially get the coloring right of some of these very gray and stark landscapes in Alaska. But he was a pro. He was a true expert in it. And so he's got some spectacular photos that are in the Cornell archives that we're working to digitize. And also just showing the amount of glacier change over time. So this is a brief outline of what we're going to talk about today. I'll talk a little bit about, starting from the beginning, since this is the first glacier talk in this series, talk a little bit about what is a glacier, why are they important, how are they changing, how we're going to find out that glaciers that are right next to each other can have very different responses to the changing environment around them. And we'll talk a little bit about why that is, why some are retreating fast, others are slow, and a few are advancing. And then we'll try to do a summary of what is the state of glaciers all around the world. And we're really relying on satellite data to be able to study all of these remote areas. But first I want to start with our cast of characters. One is Ralph Stockman Tarr, who was a Cornell professor for 20 years, made a trip to Greenland, and as I'll show you, he named a glacier in Greenland after Cornell. Made several trips to Alaska, and as I'll show you, he was really motivated by trying to understand the geology of Ithaca, which is so heavily sculpted by glaciers. Had to go to study active glaciers in Alaska to understand the processes. And he wrote a seminal book with one of his students, who I had to bring. So a lot of this is their seminal book, published in 1914, to centennials coming up, by the National Geographic Society, because they funded a lot of their original trips. And the real phenomenal thing about this is, just looking at this book, and I'll show you some pictures from it, it was really so far ahead of its time. It was really the seminal book on Alaskan glaciers for almost 60 years, until the 1970s, when people were able to start to consolidate other observations that were made. So looking through this book, it's now on Google Books, because I guess the copyright has expired, so you can actually get an electronic version. but the maps in the back are also really bad. For example, just in a digression, the maps in the back do not include Anchorage, Alaska, the largest city in Alaska, because it wasn't founded until 1914. It's pretty amazing. So Tarr is someone who, if you've walked around the campus, you might have come across some of these things. He unfortunately died very young, at age 48, perhaps related to some of the ice experiments he was doing out behind McGraw Hall in an unheated building. During the winter, he might have gotten pneumonia, is one of the theories that I've seen the Bryce put together. But as a result, there's a nice memorial. One of the nicest windows in Sage Chapel, some have told me, is a Tiffany window to Tarr's memory. And I think that there's a glacier up here. It's sort of hard to tell in the light, but I think that's there. As well as this Tarr boulder, which is behind, next to McGraw Hall, also behind the statue of Ezra Cornell. And I've got Bill Bryce made a rubbing of that to sort of talk about scientist, writer, teacher. This boulder, a relic of the Ice Age, symbolic of his research in glacial geology and the enduring value of his work, is placed here as a memorial of their friend and advisor by his students. And many people have remarked on the power of his teaching ability to really motivate students to want to do that. So the other person that's really important to our story is this photographer, Oscar von Engeln. And here's again some picture of him. This is one of his most famous pictures, which was actually taken right before the 1906 expedition, where he was testing out the camera. They got a brand new camera. That camera is actually in the Cornell archives. I haven't looked at it yet, but just to learn a little bit more about how exactly they did the photography there. But again, a nice gray day in Ithaca that was really testing out his depth of field and focus. And von Engeln's name might also resonate with some people here who might have heard of the von Engeln Preserve in the town of Dryden near Malloryville, which is a spectacular area where von took many students to look at this glacial feature called an esker. That's very clear here in the topography. All right, so rounding out our cast of characters is our current group of glaciology people at Cornell. Myself, postdoc Julie Elliott, who got her PhD in Alaska and has really been driving both the Tarr project and our remote sensing work. Our graduate student, Andrew Melkonian, here playing the bagpipes, who is doing his PhD thesis on glaciers in Alaska. And Mike Willis, who is actually going to give, I think, the third lecture in this series in February. All right, so let's get started. So what is a glacier? Well, a glacier, you can see lots of these textbook cartoons, and this is a spectacular example here from Greenland. It really shows you the different parts of a glacier and helps you try to understand their mass balance and why they would change. So up here at the higher elevations is what's called the accumulation. This is where snow lasts year-round, and that snow is then metamorphosed, changed into to ice that eventually, when the pile gets thick enough, starts to flow downhill until it reaches lower elevations that are warmer, and it melts in what's called the zone of wastage or the ablation zone. So there has to be a balance here. As the pile of snow gets thicker and thicker up here, it eventually gets thick enough that the ice starts to flow until it gets to a point where it stops. And so you can imagine different ways that you would change this balance. You could, for example, increase the temperatures down here. That would increase that zone of wastage, so it would not flow as far out. Or you could increase the amount of snow up here, and then that would make the glacier flow further out, even if the temperature down here warmed up a little bit. So there's a complicated trade-off in feeding the glacier up here, as well as diminishing it down here in the ablation zone. So this is one reason glaciers are complex. And I just had to show a movie. Some of you may have heard of the Extreme Ice Survey, or at least the movie Chasing Ice, or the documentary about a guy named James Ballog, who's, I'll show you in a second here. He's been putting cameras, again, another new technology here, sort of extending it beyond what Tarr and von Engeln could do. Cameras that could last year-round, take pictures, as I'll show you here in one of his movies, of Columbia Glacier, which we'll return to a little bit later. So this is several years of watching Columbia Glacier, and this is a glacier that's rapidly retreating. But the great thing about this is you can see the active calving front here. Of course, this is a time-lapse picture, so you can see calving events as this thing sort of retreats. And then the glacier is retreating back far enough that you kind of change the camera view. You can see spectacular images here of this glacier moving about 30 meters per day. The other really cool thing is, going through the year, you can see the snow falling both on the accumulation and the ablation zone. And in the wintertime, these moraines, these areas of rock, let me show that again because it's so really cool. So to sort of watch as you go through the year, you'll see that the snow will build up here, even in the ablation zone, and it will cover up these moraines, which are basically rock that's being dragged along as the glacier flows, and it gets covered up in the wintertime, and then all that snow melts away in the summertime, revealing those moraines again. So this is showing you the glacier both moving, which is a normal process, retreating, which is indicating this glacier is currently out of equilibrium. But then you can also see the seasonal cycle on top, where the snow falls and then melts away. And here it is, you can see it both on the mountains around and on the glacier itself. So spectacular pictures that, Tarr and von Engeln and Martin did a great job of documenting pictures with static glaciers, with pictures that were static, but these movies are really important for understanding the temporal evolution, as we'll see, are also a good complement to the satellite observations. All right, so let's talk a little bit about ice on the Earth. So currently the main areas of ice on the Earth, of course, are these two large areas near the North Pole, Greenland, which has enough ice within it to raise global sea level about 7 meters. That's a good way of trying to quantify. If you talk about how many millions of cubic kilometers of ice, but this sort of brings the point home right away that about how much ice is really up there. But of course, Antarctica is the big one, which all of Antarctica encompasses something on the order of 57 meters of global sea level. But unlikely that any of these, while over the course of the ice ages, over the course of thousands, tens of thousands of years, you might see all of this ice melt and then refreeze again. Over the time scales of centuries, some of the smaller glaciers are really important, even though volumetrically they're really not that big. So this is showing a map of all the other glaciers here in Himalaya. There's a little bit in the Alps, throughout the Andes, in the Russia, in Canada, and in Alaska, where we'll spend a lot of time today. So all of that ice, they're spectacularly large glaciers, but of course the Earth's oceans are also spectacularly large. But if all of that were to melt, it would only be about 0.3 meters of sea level rise. But the important thing is that most of these areas are at lower elevations, and currently they are contributing more than their fair share to global sea level. So just as an example of the current amount of global sea level rise, you've got something on the order of 2.5 millimeters per year. Most of that global sea level rise is thought to be due to just the oceans heating up. As the oceans heat up, they expand, and that's the bulk of current sea level rise. But this is sort of an old figure here. The glaciers, the mountain glaciers, or the temperate glaciers, or whatever you might want to call them, all throughout these areas are contributing to current sea level rise in about equal amount as Greenland and Antarctica. So even though they are aerially very small and volumetrically not significant compared to these other ones, because they are at lower elevations and lower latitudes, in many cases they are more responsive. And just to bring the point home, how important is global sea level? Well, you may have seen many news reports that talked about how the effect of global sea level rise on the impact of Hurricane Sandy. This is just looking at several cities here in the U.S. where if global sea level rise was to go up 1 meter or 6 meters, sort of impact it would have on Washington or New York or Miami. Probably on the order of time scale of the year 2100. 6 meters is probably unlikely, we think. There really is a lot of uncertainty as to how much sea level rise could really happen in the next 100 years. And understanding the mechanics of glaciers is the main source of that uncertainty. So somewhere on the order of maybe half to a full meter, and maybe a little bit more, is possibly likely by the end of the century. So you can see that would have a big impact on Miami and New Orleans and other places. All right, so what's another reason that we care about glaciers? Well, one is, as I mentioned, that motivated Ralph Stockman Tarr was that glaciers used to cover us here in Ithaca. So here's a map of sort of the last glacial maximum. And you can see covers well all the areas around here. And of course, there's this beautiful painting here in the museum that sort of shows what Hugo Lake might have looked like as the glaciers were retreating at the end of the last ice age. So understanding Glaciers, how glaciers behave, what processes are happening at glaciers is another important reason for us to study them. And then, of course, I just have to include this picture of a helicopter in front of one of the outlet glaciers of Greenland, and just say, glaciers are just an amazing phenomenon on the Earth, and this is the reason tourists go to see them, because they're awesome. All right. So next thing I want to talk about is here's Columbia Glacier. Columbia Glacier is here at Prince William Sound in Alaska. An interesting side note is, as we showed you, Columbia Glacier has been retreating since around 1980. And some of you may remember, I think most of you in the audience, remember the Exxon Valdez oil disaster here in Prince William Sound. The story that was that the ship went aground because it was trying to avoid an iceberg that came off of Columbia Glacier. So there was some impact of this rapid retreat and active calving front of Columbia Glacier here. So we'll take a closer look at that. And then we'll look at some of these other areas that are behaving a little bit differently. So let's see how good these pictures look. These are a couple of pictures here from the Tarr and Martin textbook, or book about Alaska, published by the National Geographic Society. And I'm not sure, I have to find out, that if these guys were the first ones that tried to take pictures of glaciers and superimpose various monuments next to them. This is something that James Babelow currently calls the cheesy pictures, but it's really the only way to get a sense of perspective when you're looking at something that's so far away. So this is not the Washington Monument, this is actually the Bunker Hill Monument. Still 220 feet tall, so, and this is showing a picture of the active glacier front, and they saw this big ice tower that the caption says collapsed just after the picture was taken. So they also showed a picture, this is up the front of Columbia Glacier, and this is another picture of Columbia, or sort of a drawing of Columbia. In this case, they've superimposed a map of the District of Columbia on top of Columbia Glacier to give you a sense of scale. And they say something like, anyone who's walked in the city of Washington will appreciate the size of this thing. So here's the Capitol, here's the Pennsylvania Avenue going, here's the White House. Just giving you a sense of the size of this glacier. So this was a way that some of these pictures were published in the magazines of National Geographic, but not all of them. All right, so here is a picture showing basically the stable front of Columbia Glacier around 1980, and then more recent pictures that have shown about the 20 kilometers of retreat of this glacier over time. One interesting thing to say, let's see if we can fire this thing up, was that when Tarr went to visit Columbia Glacier, it was in more or less a stable condition, but it also showed some episodes of advance. So let's see if we can get that to work here. All right, so here is one of von Engeln's pictures, I believe this is 1909, showing the front of Columbia Glacier. And maybe you can sort of see here that there is a man standing, and this is a push moraine at the front of the glacier as the glacier is advancing just a little bit. It was not in the major period of advance, it advanced maybe a few hundred feet. But this is just one sign of evidence of that advance. Another sign of advance that they have numerous pictures of, let's see if I can is that it ran over some trees. All right, so here is an example. It's sort of hard to get a sense of perspective here, but this is, again, Columbia Glacier here in the background, and they have several pictures from several different angles of the glacier basically overrunning the trees in front of it. Sometimes the trees were pushed from their root system back on top of the glacier, sometimes they were just knocked down completely. But this is just giving you some evidence that in 1909, this glacier was here on this island. These pictures are taken here on this island called Heather Island, where there were some periods of advance and retreat in the scale of a few hundred meters, or a few hundred feet, I should say, over the course of their various visits there. There was visits in 1899, and 1905, 1909, 1910, where it was sort of more or less stable, little periods of advance, and then all of a sudden around 1980, a catastrophic retreat began. So we'll try to talk about a little bit why Columbia all of a sudden did this, but I guess one question to ask is how do we know what Columbia is doing and how do we quantify it and compare it with some of its neighbors? So our work at Cornell is focused on using remote sensing observations, and we use a variety of different kinds to study glaciers in different ways. So one thing that we try to measure is basically the height of the glacier. How high is the glacier and how is its height changing on its time scale of days or years. The other thing that we can measure from space is to use repeat images to measure how fast the glacier is moving, how fast it's changing with season. The final thing is a new technology that it uses gravity. That basically has, as I'll show you, a pair of satellites can measure changes in the Earth's gravity field. So as ice is gained and lost during the course of a year, we can measure how much that is and compare different glaciers. All right, so let's walk from Columbia over here to Glacier Bay. And here is a picture of what Glacier Bay was when it was sort of first observed by Westerners. This is an inference, as I'll show you how this was made. Basically coming here to the mouth of the glacier, with a glacier sort of covering this whole area. And this is more or less what Glacier Bay looks like today. It's retreated extensively. In fact, it exposed this new watery area here that's now called Tarr Inlet, after Ralph Tarr. And over the course of many decades, Tarr and others have documented how, with pictures, how the glaciers have retreated this is again showing over the course of several hundred years. So in this case, the glaciers have thinned significantly, and you can actually use measurements to infer that thinning. And so I guess one thing I should have pointed out here is that as you watch this, maybe you could even see that as the glacier thins and disappears, you can see a bunch of bare rock. Right? So the bare rock indicates where the glacier used to be, and you can measure this position. It's called a trim line, where the vegetation ends, to measure how thick the glacier used to be. And so that can be used in all these areas of rapid retreat. This is taken by a glaciologist at Alaska called Chris Larson, again showing trim lines here in Glacier Bay. And if you go around the whole bay and measure the trim line position, that's what all these little red positions are, that's how they were able to make these past inferences of how thick the glacier was in different parts of Glacier Bay. And so this is what they infer that it used to look like, with ice thicknesses up to a kilometer to a kilometer and a half in some areas. And again, all this material has now diminished. It's sort of combined over the course of several hundred years, contributed about a centimeter of sea level rise, but at a massive amount. And so, as you can see, this area used to be covered in glaciers, but some people have proposed they now call it Timber Bay, because the glaciers are still there, but most of what's in here is now wood, as the forests take over the areas that used to be covered by ice. All right, so remember, Columbia Glacier is an area of rapid retreat. Glacier Bay is another area of rapid retreat. The ice field just to the east of it, here near the capital city of Alaska, Juneau. I'll show you a little bit of evidence of the complex behavior that's going on here. So just a brief qualitative understanding of what we're doing with measuring glacier heights with satellite observations. Trim lines are a spectacular thing to use, but usually you need to have a significant thinning of the order of hundreds of meters to be able to see a trim line. If you wanted to measure how much a glacier was changing its thickness on a year-to-year basis, we're going to use basically just topography maps. So we're using a satellite launched by NASA called the Terra satellite, and it actually has on it a stereo camera. It has a camera pointing straight down and a camera pointing back. And so using the stereo images, you're able to create a map of elevation called a digital elevation model. And so we have, every time the satellite overflies, and it's cloud-free, which is pretty rare actually in Alaska, unfortunately, but it's acquiring images almost on the order of every 16 days, so we can always get a few clear cloud-free images a year if they turn the satellite on for us. And we're able to combine all of these different maps together. We sort of make sure they're aligned. Some of people like to say this is like aligning a stack of pancakes. You basically want to make sure that they're all pointing in the right spots, and then we try to difference how much elevation has changed in each pixel within these images over time. And so once these things are aligned, we basically, for each pixel within here, we look at the elevation as a function of time to see whether it's thinning, whether it's thickening, or whether it's more or less constant. Just to give you a sense of what we can achieve, this is an example from Patagonia, but an area that is rapidly thinning like some of the glaciers in Alaska. So this is showing you over the course of 9 years, sort of go back and forth. This is a glacier that has retreated about 4 kilometers, but thinned about 450 meters, which is about the height of the Empire State Building. So not all the glaciers in Patagonia are doing this, but this is just giving you a sense of using two digital elevation maps, how are we able to map the thickness change? And it's mostly happening here at the front. Maybe you can see that the areas back here are not changing as much. All right, so we've done that here for the Juneau ice field. We've made a map of elevation change. So again, the city of Juneau is right about down here. I don't know, have any of you been to Alaska to see Mendenhall Glacier? I have not myself, but my parents took one of those cruises up there for their retirement. And this is the one glacier that everyone gets to see here at Mendenhall. It's been well studied for a long time because it's so close to the city of Juneau. But this map here is showing you thickness change with areas are red or areas that are thinning, areas that are blue or orange are either thickening a little bit or null values. And you can see that almost all of these little glaciers that are coming off the main ice field here. This is sort of the area of highest topography, and these are the areas of lower topography. All these areas that are these outlet glaciers are thinning, with the exception of this big one, the biggest glacier on the ice field. This is one called Taku, which is actually thickening just a little bit and also advancing. So this is an example here of a complex relationship between a lot of glaciers are thinning, one glacier is thickening, but the overall effect from this particular ice field is just slight mass loss for the whole thing, while some of the other glaciers in Alaska are thinning a little more rapidly. And this is just giving you an example over here of looking at individual pixels to say, here's how fast this area is thinning on the order of 4 meters per year. Some of these areas are pretty much close to neutral. The area that we looked at in the last example from Patagonia is thinning on the order of 20 or 30 meters per year. So that's an extreme example in comparison. All right, so what does Columbia Glacier look like for comparison? Again, this is Columbia Glacier, which has been rapidly retreating over the course of the last 30 years. Again, it's thinning on the order of about 10 meters per year. But within this area here around the Chugach Mountains in Alaska, you can see that almost all the glaciers, again, are retreating. But there's one glacier here in College Fjord. This is Hubbard Glacier. This is Yale Glacier. Hubbard is advancing, Yale is retreating. And this is, of course, named after Columbia University as well. It's also vastly retreating. And this has been known from the ground observations as well. So this is a picture taken by one of the people that actually worked in Alaska with Tarr, named U.S. Grant, worked for the U.S. Geological Survey. And there's a guy named Bruce Molnia who gave a seminar here on campus just a few months ago, whose main job has been comparing from exactly the same position pictures from the past with pictures from the present or recent past. And so you see that he worked very carefully to return to this area in the year 2000 and align these two pictures and show that, in fact, this is one of the few glaciers in Alaska that actually is advancing and sort of has blocked off Radcliffe Glacier over here. You can't see it from that same vantage point. So just as an aside, we had to mention, well, what about Cornell Glacier? Why didn't Tarr name any glaciers after Cornell? Well, he'd already done it in Greenland. As part of this trip in 1896 by some of the faculty at Cornell, that went with Perry. This is the time of the trip they went to retrieve the York meteorite, which you can go see in the American Museum of Natural History. The Cornell group went off on a side trip here and named one of the mountains after the Cornell president and a glacier after Cornell here in Greenland. All right, so now let's talk a little bit about why. Why is Columbia Glacier retreating so severely? Hubbard Glacier is advancing, Taku Glacier is advancing, and Glacier Bay just underwent this catastrophic retreat. And the key thing to say is that there are lots of different processes that are operating on glaciers, and so there can be some difference in how they are responding to climate depending on the local geographic conditions. So as I already mentioned, glaciers eat and grow from the amount of snow accumulating in their accumulation zone, and they routinely melt away and waste away here by having, in the ablation zones, by having a change in temperature. But particularly glaciers that are called tidewater glaciers, these glaciers that come off to the ocean like Columbia Glacier and Hubbard Glacier and so forth, have additional factors that can be at play. One is that as there's increased melt, there can be a feedback to that water escaping to the bottom of the glacier and causing the glacier to suddenly speed up or slow down as that thing would be cut off. Similarly, the rates of calving can change, and that definitely has been an important role in the retreat of Columbia Glacier. And as the ocean water can change temperature over the course of the season, as currents of warm water might come in and help to eat the glacier away from underneath. So amount of climate change in the air in terms of changing snowfall and melt is definitely can have a big factor, but all these other things can also change with time as well, and that's why adjacent glaciers can sometimes have different responses. And in particular, what's probably happening at Glacier Bay and in Columbia Glacier is one of these instabilities that's called the tidewater glacier cycle, where the idea is that at some point when the snow accumulation in the area has been enough, the glacier is driven forward, it pushes forward, it pushes its little moraine at the front forward, and pushes it all the way out to here in the ocean, which is what you can see here in 1980, sort of a moraine out here of junk that has been dropped by the calving glaciers that builds up this pile of sediment, and this is where it stays. As I said, it sort of had stayed for over 100 years. Tarr saw it at the same location as Landsat sees it here in 1980. But if there's just a small perturbation, if the glacier starts to retreat just a little bit, then the water can start to come in underneath the glacier and start to eat it away and make it melt a little bit faster, and then you can sort of have a very rapid retreat until it gets to another point where it can sort of be protected and be stable. But that often happens that it retreats too far. That it retreats too far for the amount of snow it's getting at the top, and so that's why these things will then start to advance again after that sudden retreat. So there's some predictions that Columbia Glacier should stop retreating in by the end of the decade or thereabouts, and presumably if the snow accumulation is not too different then as it is now, it might even start to advance a little bit after that, after it gets to some sort of stable point. So this is why there can be a sudden retreat, and the question is, well, you know, if there's this sort of inherent instability in the shape of the glacier, how important is climate change versus just the natural processes that are happening? Well, the key point is that as the climate warms in this area, the glaciers thin. And so even though this is a natural instability in the glaciers, the fact that there's thinning related to warming has made the glaciers even more unstable, and so as that sort of perturbation at the front of the glacier occurs, this glacier is thinner, it's more likely to be floating, and allows more water to come underneath. So there is always a natural instability in many of these glaciers in advancing and retreating, but global warming sort of tips the scale in favor of making that a little more extreme and more likely to occur. All right, so how do we test ideas about glacier advance and retreat in these sorts of cycles? Well, that's where we're going to use our next set of spacecraft observations to test that. So again, this is a map of that same glacier called HPS 12. It's just a glacier named after, in Spanish, the name of the Hielo Patagonio Sur 12. And so it's a pretty small glacier, hadn't been considered that important, but it is rapidly retreating. And I sort of look at it here to look at, you can look at two different time periods, in this case, within within 1 week of each other, just so you can sort of see with your eye that crevasses are moving. You know, this glacier is moving on the order of 20 meters per day in this area down here, and you can sort of see, even with your own eye, that if you look at repeat imagery, you can watch that glacier move. So we're able to apply that technology to both optical images and radar images to look at glacier motions throughout Alaska here to figure out how the glaciers are changing from year to year, but also how the glaciers are changing over the course of the season. You might expect that as the spring melt season comes around, you have more water percolating down to the bottom of the glacier. The glacier will speed up temporarily and then slow down once that pulse of spring melt ends. But again, glaciers can surprise us with their complex behavior. This is an example here of Hubbard Glacier in Alaska, in Yakutat Bay, which is a glacier that likes to advance and retreat. And when it advances, it can sometimes block off this area over here called Russell Fjord and turn it into Russell Lake. And it did this last time in the 1980s. And you can imagine that when it's blocked off, this is seawater, and as it's blocked off, it causes an increase in the amount of fresh water in that lake then, and that can be very hazardous to the sea life that's in that area. But before too long, that that dam of the glacier was broken, and again, currently it has the ability to communicate with the open ocean. But it's in currently a period of advance again, and this is showing different maps of velocity here in the course of the winter, in the course of the spring, and in the course of the summer, showing you velocities in this case of up to 8 or plus meters per day in this area. And you can see here the interesting thing that the glacier, sort of hard to get a good measurement here, but the glacier is actually sped up during the summertime in this part over here. But the point out here near the terminus of the glacier is actually slowed down. In the winter, it's actually faster than the summertime. And so this is sort of a surprising thing where you would think in the wintertime there would be less melt available to lubricate the glacier to make it go faster. But we see the fastest speeds, or among the faster speeds here in February through March, and slower speeds here in August. And so trying to understand the mechanics of how that works, one idea is that it's not just the quantity of melt that is important, but if the melt is freely flowing at the bottom of the glacier, it might be draining so quickly that it's not having an impact on lubricating the glacier. And so that's one hypothesis as to why the glacier might actually be going slower in the summertime than it is in the wintertime. And again, I'm going to show some pictures that Tarr took of Hubbard Glacier and his studies here in Disenchantment Bay. But this is one of the pictures from their book that I think this may have been a case of feeling a little bit of North American inferiority compared to Europe. They took the biggest glaciers in Europe and they put them all here on top of Hubbard Glacier to show. This is in fact one of the largest glaciers in North America. It's about 76 miles long, but compared to the glaciers of the Alps, they aren't much to look at. So Tarr actually spent a lot of time here at Hubbard Glacier, as well as some of the other glaciers in Yakutat Bay. He returned there year after year and wrote several papers, both on the glaciers there, as well as their response to some of the earthquakes. There was a large earthquake in 1899, and some of the glaciers were seen to advance after that earthquake, so he wrote some papers that were on the theory of glacial advance. So I'm just going to include a couple of pictures here that I liked of Tarr and von Engelen's work in Hubbard Glacier and Yakutat Bay. So this is a picture on top of Hubbard Glacier. So I'll show you a picture of Hubbard Glacier here in a second, but you can see here this is basically a moraine on the edge of Hubbard Glacier. So there's a mixture here of ice and rock, and a little bit of a stream coming through there as well. And let's show you, I love this picture here because it really gives you a sense of what fieldwork was like in 1906. This is the boat that they're using here to basically travel from their camp across the fjord to study Hubbard Glacier. Let's see, here's a good picture of Hubbard Glacier itself. All right, so here is a picture of the top of the glacier, and here's a picture of their camp. And doing field work, and actually, so how they were able to get to Yakutat Bay by taking the train from Ithaca over to Seattle, and then they took a steamship, taking a lot of the old gold miners up to Alaska. So they had lots of adventures on their steamships and a lot of interesting characters. But here's a picture of their camp, looking across the fjord here over at Hubbard Glacier. And so this is some of that moraine that they were just walking on.
Did they at first, was fun first to use this particular camera for this purpose?
Not exactly. So there are some people, so Harry Fielding Reid, as well as the Harriman Expedition in the 1890s. I'm not sure if they took a lot of pictures there, but they didn't go everywhere. So
These pictures are.
all right, so here's a picture of them standing here next to the fjord as well. And here's the last picture we got of Hubbard Glacier. I have to say that I just spent an hour looking through lantern slides. These are just ones that I grabbed. There's a rich collection. So here's another picture of Hubbard. Again, showing the glacier coming down. Here's a very narrow fjord and the moraine that they were walking on in one of their other pictures. All right. So think I have just a couple more slides I'll show you here at the very end. All right, so we talked about measuring glacier height and glacier height change with time. We talked about measuring glacier velocities and velocity changes with time. One of the great innovations over the course of the last decade was measuring gravity. And gravity changes with time using this pair of satellites launched by NASA and the German Space Agency. They're called Tom and Jerry. They basically track each other's position very precisely with this little radar in between them. And what that does is, as they're going over the Earth, they can move closer together or further apart depending on the gravity of the ground. And so they're doing that, and they're able to make monthly maps of how the gravity is changing. Over given parts of the ground, they might speed up more in one part of the year versus other times where they might not be attracted as much as other times. And so a variety of processes have been studied by this. This is a particular map isolating out the gravity change signal just related to land ice. So if you remember the map of land ice before, there's a lot of change here in the mass of the glaciers in Canada. A little bit less change here in Russia, or big change here in Svalbard, Iceland, Himalayas, and of course big changes here in Patagonia and Alaska. So this is sort of the quality of the map. You can see it gives you a very broad picture over the course of several hundred kilometers, telling you about the amount of mass that's being lost, but it doesn't necessarily give you this detailed picture on a glacier-by-glacier basis to tell you which glaciers are advancing and which glaciers are retreating. But it's a good complement to sort of use all of these different methods together to make sure we're not fooling ourselves about the rates of mass loss. So here's the end. We're going to talk take a little tour of the world's ice masses and talk about their state of health that we've been able to learn from these remote sensing tools. So again, here are Greenland and Antarctica, and typically people break up Antarctica into 3 different parts because each one seems to have a different pattern, and I think that's fair just considering the large size of Antarctica here. So there's East Antarctica, which is usually high and colder, West Antarctica, which many people worry about as being an area that might undergo rapid retreat, and then the Antarctic Peninsula here, which goes a little bit further north, which acts a lot more like some of the mountain glaciers just because it's not quite as a polar terrain. And so this is just showing maps of mass loss for Antarctica from these different techniques, and measuring the height change, measuring velocity changes, and then correlating those into the amount of mass that would be lost, and then looking at gravity change. So the interesting thing here is you can see that each of these different techniques has slightly different spatial resolution here. Gravity looks a little bit blurrier because it has this large footprint that it measures on the ground, but they all have a general sense that East Antarctica, if anything, might actually be gaining a little bit of mass. You can see these areas of red here that mean that there's extra snowfall there that isn't being lost. But here in West Antarctica, all of these areas, all of these techniques are showing significant mass loss. So if we break down these areas of Greenland, East, West Antarctica, and the Antarctica Peninsula, and compare them with mountain glaciers, we then can compute the amount of mass balance, here shown in gigatons per year, of how much ice is being lost in a net sense. So as I mentioned, 0 here would be incomplete balance, which is sort of what you would, if the amount of snow falling and the amount of ice that's melting at the ablation zone is in balance, then this should be about 0. If there's too much snow, it would be positive. If there's too much melt or outflow, it would be negative. So you can see here Antarctica is, East Antarctica is probably a little bit positive. The Antarctica Peninsula is slightly negative. West Antarctica a little more negative. But the real big losers in terms of ice mass are Greenland and these mountain glaciers. So again, the mountain glaciers are really small in terms of aerial extent. And for those of us that study mountain glaciers, I guess you could say we have a little bit of an inferiority complex compared to these big ice people who say our ice is the biggest. We can give you 60 meters of sea level rise, but on time scales that are relevant for planning purposes over the course of the next 100 years, these mountain glaciers are significant. They're probably sub-equal to Greenland in terms of the current contributions to sea level rise. So just in terms of a summary, this is just showing a map here focused on Greenland and Antarctica, showing over the course of the last few decades how sea level rise is being contributed from these different things, different ice sheets. We have about, you can see a little bit of acceleration here from the 1990s these two ice sheets were contributing about 1/3 of a millimeter per year, and currently they're probably more on the order of 1 millimeter per year, and if we include the mountain glaciers as well, probably around 1.5 millimeters per year out of that 2.5 millimeter total, which of the sea level rise, where the rest of that is being made up by just heating the oceans up and allowing them to expand. All right, so let me just give you a summary here. I'll show you a couple of last slides. Satellite observations are really critical for trying to measure all of the ice in the world. And there's some great stories of, there are long records of people going out and digging snow pits in particular glaciers and measuring the amount of snow that falls every year, and also going down to the ablation zone and pounding stakes in there and measuring how far the ice melts every year. And those are very detailed field studies that sort of validate these observations, but those field studies can only be done on a few glaciers that are accessible, where the manpower exists to be able to go out and make those measurements. And those, in fact, what recent studies have found is that most of those field studies had been picking glaciers that were preferentially changing more. So in fact, those field studies were then being extrapolated to all the glaciers on Earth, and they were predicting a little bit more demise of ice than actually the satellite observations showed. So while those field observations are important ground truth for the satellites, to be able to look at all the ice and make sure that we're not just extrapolating from a few observations to the whole world, they're really key. Glacier melting from both Greenland, a little bit from Antarctica, and mountain glaciers, contributing about 60% of the current sea level rise. And a key unknown, key area of research and interest is trying to understand how fast will the glaciers change over the course of the next 100 years. And as we talked about, the response of individual glaciers is complicated. Some of the changes is related to climate, some is not, and understanding these on a glacier-by-glacier basis is really an area that we're working on for the research. And the final point is, we think that the Von Engeln and Tarr photographic collection is really valuable scientific tool for looking at the historic state of these glaciers and understanding how they've changed over the course of the last 100 years or not. And in fact, this has been confirmed by, as I mentioned, Bruce Molnia actually spent a year at Cornell around 1969 working with Art Bloom and others. And he's made his life work, and one of his key things is to say, the Tarr collection has been in the Cornell archives for many decades and has not really been subject to scientific study. And if there's any sort of mass of historic documents out there that really help us add new information about the historic state of these glaciers, this is the place to go. So that gave us enough confidence to have a bunch of undergraduates help us sort through that during the fall semester here. I didn't show their pictures because they've only been working for a few weeks. We haven't had them all together for a picture yet. But there really is over 1,000 film negatives and glass slides that we're trying to figure out ways to digitize them, and I don't know a lot about digitizing, so we're trying to learn. And this is also a picture of Tarr from 1909 from one of the Cornell publications. All right, so let me just end with a couple more pictures here from Tarr in particular. So this is a couple of pictures from the Greenland Expedition of Cornell Glacier, again showing, these are actually pictures, as far as I can tell, were actually taken by Tarr, according to the lantern slide notation, which, so this is again from 1896. Quality has degraded a little bit more, but again, this is their camp, and this is Cornell Glacier in the background. And this is a picture from on top of the ice field, showing the top of Cornell Glacier. So these are a little bit more washed out than the earlier pictures, but there's a good collection of pictures of Cornell Glacier that exist, and we'll have to go through them and find the best looking ones. But great, well, let me end there and take any questions you guys have. Thanks for your attention. Yes, thanks, Rob.
What is the primary sort of quantitative data that you can get out of these lantern slide collections? I mean, is it primarily sort of verifying in a qualitative sense, or is there a suite of measurements that can be made that are helpful at getting into this century-long scale?
That's a good question. So in terms of what quantitative measurements could be made, certainly what you're measuring is terminus position. And as we talked about, the terminus position can actually move without causing a lot of thickness change in the glacier as well. And so you want both the location of the terminus as well as some information on the height. And so I don't really know how well you're going to be able to do both of those things. But I think to some extent what you're going to be able to do is be able to characterize some of these glaciers. The key question we're asking right now is, are there glaciers that have not been visited from the same vantage points since 1905, 1906, or whenever these observations were taken. So that's what we're focusing on right now that we have a list of all the locations where the slides were taken, trying to figure out exactly what the vantage points were, just to get some assessment of, starting with the amount of retreat. And so that's our current task, is just to figure out what's there. And the amazing thing is that because of Tarr's untimely death in the spring of 1912, the photographs from their 1911 field season were pretty much never used for any publications. So in particular, we think that the observations from 1912, where they went to a bunch of places that they had not gone in previous years, particularly Taku Glacier and some of the ones in the southeast, I think there's a good potential that we might be able to at least map change in terminus position. But as you say, trying to get quantitative measurement of volume change and things like that is a little trickier to do, especially since Tarr's handwriting appears to be horrible. And reading his field notebooks, I think Bill Bryce I don't know how in the world he was able to read those old notebooks, but we haven't had a lot of success with that.
So do you have a team of people also planning, is it Molnia that would go out and take additional photos based on these new ones? Or?
Yeah, that's a key question. I think our thought process was that we wanted to see if there was compelling places that we might look into that, and then go back and remind the National Geographic Society that they had funded this work originally, and then this would be good for them to fund follow-up investigations. So that was our plan, if we could find good locations that we want to go back to. Go ahead.
You mentioned that in the East Antarctica there seems to be an increase in snowfall.
Mm-hmm.
Do people think that's related to a warming climate?
I think, I'm not an expert in Antarctica, but that's at least the story, is that as the atmosphere warms, it can hold more water vapor within it. And so that water vapor could then fall as snow in some of these really cold areas. So that was always the question, as to how much that trade-off between more water vapor in the atmosphere possibly falling as snow would trade off against increased temperatures. And so in general, it seems that the increased snowfall has been observed in some places, but the amount of melting has increased even more. So that has been a trade-off that's led to recession, except in this case of East Antarctica, which is one of the coldest. It's a really high altitude place. It's really cold. So they're probably, it's a polar desert. So I think that in general it was always snow limited over there. And so the increased warming might actually, have the increased amount of accumulation there might not be as much melt there. And so the balance might be in the favor of accumulation, at least for that spot. But you can see that it was a relatively small increase compared to the amount of loss in a bunch of these other spots.
Could you go to the elephant foot slide?
Sure.
That's the one that I realized that I don't understand. I don't know the definition of what is the glacier and what isn't the glacier.
Okay.
It seems like that's a good slide.
Yeah, I think that what you're going to find is a lot of people debate exactly what are the right terms to use.
Yeah.
So in this, there's different terms that are used. There's ice sheet,
Yeah.
ice cap, and glacier. And so ice sheets are pretty much the whole Antarctica, the whole of Greenland, that Laurentide ice sheet that covered us. And, something that is millions of square kilometers in size is an ice sheet. But off of that ice sheet, there can be these little protrusions, these outlet glaciers. And so that's what you're seeing here is this is all part of the Greenland ice sheet up here, and then these little glaciers that come off the side would be, glaciers that are part of the ice sheet. But in addition to that, there are also these smaller glaciers like we see in Alaska that aren't attached to an ice sheet per se. Some of them might be, you know, relatively isolated. Some of them might be attached to larger ice fields, like around Juneau. But does that sort of answer your question about
It does. So I mean, I guess the question would be at the first question. I would say sort of where does the ice sheet end and where does the glacier begin? And you're saying that's a bit fuzzy.
Exactly.
Yes. And I think the answer to Rob's question,
Yep.
answers this for me, but I'm having a hard time understanding sort of what is noise on the advance and retreat.
Sure.
And it almost sounds like the answer really depends on, well, I'll let you answer. Like
You mean in terms of noise, in terms of natural variability?
yeah, natural variability where if somebody said to you, you know, it's advancing X amount, you said, no, it's just noise.
Well, I mean, the important, I mean, in terms of when we make these measures of mass balance for the whole ice sheet, you know, we account for that advance as well as the retreat. So, I mean, we sort of imagine that most of that advance is due to this natural variability. That, you know, these glaciers, these outlet glaciers go through these cycles of retreating too far and then re-advancing to get back in equilibrium. And so that, I guess you would call that sort of the noise, which is the natural variability. And how do you separate that noise from the longer term trends? And that's a major question that reviewers of our scientific papers are always asking us to verify, especially when you only have records that go back 10 years, like these satellite records do. And so, you know, it's hard to say. We have, you know, we all know that you have some years that have more snowfall than other years. And so how does that feed into understanding natural variability? And that's why you want to have these multi-decadal records that go back to the pictures of Tarr to try to understand, you know, what is natural, sort of extents ranges of variability, and you know that ranges of variability is changing with climate because some people say the extremes, you know, the amplitude of the extremes changes as you warm up the world. You have the years of heavy snowfall become heavier, and years of melting become more extreme as well. So, I mean, it's a difficult problem to disentangle all those things, but those are things we're struggling with whatever records we